How do you maintain state across multiple function calls without using global variables or classes? Closures are the answer. A closure is a function bundled with its surrounding state. This state is called the lexical environment. Let us define a function factory named makeCounter. This outer function initializes a count variable to 0. It then returns an inner function. The inner function increments and returns the count. Crucially, the inner function retains access to count. This happens even after makeCounter finishes executing. We call makeCounter to create two separate counters. Counter 1 and Counter 2 are independent instances. Calling Counter 1 multiple times increments its retained count. Counter 2 maintains its own independent count variable. This retention mechanism defines the closure boundary. It allows us to create private, persistent state for function instances. JavaScript uses lexical scoping. Scope is determined when the function is defined. It is not determined when the function is executed. When a function is created, it captures variables from its immediate outer scope. This captured snapshot forms the function's lexical environment. When the function runs, the interpreter searches for variables. This search follows the scope chain. The search starts in the local scope. If the variable is not found, the search moves to the closure's lexical environment. The chain continues upward until it reaches the global scope. Consider a nested function example. The inner function accesses variable A from its immediate parent. It also accesses variable B from the grandparent scope. The scope chain facilitates access to both A and B. Understanding this lookup process is fundamental for debugging scope issues. Closures are the primary tool for data encapsulation in JavaScript. They create private variables inaccessible from outside the defining scope. We implement the module pattern using an immediately invoked function expression. This IIFE executes immediately and returns an object. The returned object contains public methods. Inside the IFE, we define sensitive data, such as a user token. This token is now a private variable. The public methods like getToken and setToken are defined within the closure. These methods are the only way to interact with the private token data. This structure enforces controlled access. It prevents accidental modification of critical configuration settings. The IFE scope protects the internal state. This pattern is widely used for creating singleton objects. It is also used for managing application state securely. Closures are crucial for implementing functional programming techniques. Currying transforms a function taking multiple arguments. It converts it into a sequence of functions. Each function in the sequence takes only a single argument. Let us define a multiplier function. This function takes the factor x as its first argument. It returns a new function. This returned function takes the number y. The inner function closes over the factor x. This allows us to create specialized functions easily. For example, we define double equals multiplier 2. We also define triple equals multiplier 3. Double and triple are reusable, context-specific functions. Partial application fixes only some arguments. Closures retain the fixed arguments for later execution. This enhances code reusability and readability in complex pipelines. Closures are implicitly created when assigning event handlers inside loops. Using the var keyword often causes the stale variable problem. Demonstrate a loop using var to attach click handlers to 3 elements. When clicked, all handlers reference the final value of the loop index. This happens because var is function scoped, not block scoped. The correct solution uses let inside the loop. Let creates a new block-scoped variable for each iteration. This ensures a unique closure captures the correct index value for every handler. Alternatively, wrap the handler assignment in an IFE. Pass the loop index as an argument to the IFE. This explicitly captures the index value at the time of iteration. Always prefer let in loops to avoid unexpected closure behavior. The primary memory consequence of closures is variable retention. If a closure persists, it prevents garbage collection of its retained variables. If a closure holds a reference to a large object, that object remains allocated. This happens even after the outer function has completed execution. This retention mechanism increases memory consumption significantly. Consider a scenario where a closure references a massive array. This array is defined in the outer scope. As long as the closure function is reachable, the massive array remains in memory. The JavaScript engine cannot free the memory. Developers must be aware of this potential for memory leaks. Unnecessary retention of large data structures impacts application performance. Developers must actively manage memory when closures retain large, unneeded objects. To mitigate memory leaks, explicitly set retained variables to null. Setting the variable to null breaks the reference chain. This disconnects the closure's lexical environment from the large object. The garbage collector can then reclaim the memory. Implement a cleanup function within the module pattern. This cleanup function sets internal references to null. Execute this cleanup when the module is intended to be destroyed. This practice is vital for long-lived components. Failing to detach references leads to gradual memory accumulation. Always provide a mechanism to explicitly release retained resources. This ensures efficient memory usage over time. This prevents performance degradation in single-page applications. Asynchronous operations fundamentally rely on closures to maintain context. When a callback is passed to set timeout, it forms a closure. This closure captures variables available when set timeout was called. The same principle applies to promises and fetch requests. The callback executes later, often long after the surrounding function returns. The closure ensures access to necessary state variables. These variables might include request identifiers or user data. Without closures, the callback would lose access to its required environment. This mechanism bridges the gap between synchronous definition and asynchronous execution time. They are essential for managing state in modern web applications. When defining closures, only reference the specific variables required by the inner function. Avoid capturing the entire scope object unnecessarily. Minimizing captured variables reduces the memory footprint retained by the closure. Prioritize using let and const over var in all blocks. Block-scoped variables naturally limit the scope captured by subsequent closures. This reduces the risk of accidental retention. Always implement explicit cleanup mechanisms for long-lived closures. This is especially true if they reference large data structures. Use weak references if the retained object should not prevent garbage collection. Regularly audit your code for unnecessary variable retention in persistent closures. Efficient closure management is key to high-performance JavaScript.